Hello, and welcome to this episode of the Geotechnical Engineering Podcast. In today's episode, we'll be talking with Dr. L. Sebastian Bryson, Ph.D., P.E., DGE, and Fellow of the American Society of Civil Engineers, the current Harlan Warnick Wan Professor of Civil Engineering in the Department of Civil Engineering, and he also has a joint appointment in the Department of Earth and Environmental Sciences at the University of Kentucky, and he's also the current department chair. Dr. Bryson will share insights in utilizing satellite data to assess and predict landslides, and also discuss some of the challenges and limitations encountered when utilizing satellite data for landslide assessment and prediction. I'm your host, Jared Green, and I'm excited to be bringing you another episode of the Geotechnical Engineering Podcast. But before we get started, here's a quick word for our sponsor from today's episode, that being Simpson Strong Tie.
I think my biggest struggle was I knew I was gifted but didn't know how to use my gift. My boss at the time encouraged me to go back to school through Simpson's education reimbursement program. Simpson said, hey, we see where you are, we see where you want to go, we'll put you on the path to get there. Actually just recently finished my MBA degree. I like that Simpson cared about my personal goals as well as my professional goals. They gave me the space to develop who I was becoming.
Welcome to the show, Dr. Bryson. How are you doing?
I'm well, thank you. Thank you very much.
It's good to see you again. I've been looking forward to this conversation, so I'm so glad that you could carve out some time for us. This should be a lot of fun.
Yes.
All right, well, it'd be great if you could give us a little bit of an overview on your background, talk a little bit about your expertise in the field of civil engineering and geotechnics.
Okay, thank you. Okay, so I'm Sebastian Bryson. I'm originally from Rome, Georgia. So I'm a Southern boy, born and raised. I went to school at Florida A&M in Tallahassee. Got my Bachelor's of Science in Civil Engineering there at the FAMU FSU College of Engineering. I got my master's at Howard University in Washington, D.C. And then I started working for C.H. Twom Hill, now Jacobs Engineering, for about 6 years. And then I went back to get my Ph.D. and I got my Ph.D. at Northwestern. I first started teaching at Ohio University, and now I'm teaching here at University of Kentucky, where I'm actually the department chair here in the civil engineering department here at UK. And I've been here at UK for 17 years. My area of expertise traditionally is deep excavations, excavation support and retention systems. As of the last 5 to 7 years, I've migrated into landslides and landslide hazards, specifically using remote sensing techniques to assess and predict landslide hazards. And so that's what I've been doing for right now as far as my expertise and background.
All right, great. Thank you so much. A lot to unpack there. So department chair, excavation support, GeoHazard. So there's a lot of things that you're doing. And oftentimes, you know, I find that, not to show favorites, but some of my best experiences that I had as a student was when I had a professor that started in consulting, that had some practical experience. So I'm sure there's a lot that you bring to the classrooms there.
Yeah. It's been my experience that, you know, that usually when you have a professor, one of our colleagues has kind of gone straight through, unless they've had some type of activities that involve some consulting, they miss that element. Yeah. I find myself many times in the classroom telling students, hey, I know it says this in the book, but let me tell you what we actually did in the field. So I've actually come across this before, and you do it like this, or you do it like that. Or that factor of safety is extremely conservative based on bam, and you bring in some of your consulting background, and that seems to be beneficial to the students, and it's also it reaffirms to yourself that your experience means something, right? Because you will get some academics that will poo-poo some of the consulting experience, but the consulting experience does bring an added dimension to the classroom.
I agree. Let's talk a little bit about the so geohazard assessments. Can you
Mhm,
explain that?
mhm.
Explain the concept a little bit, and then prediction, and how does it relate to your current research on landslides?
Okay, so now in the grandest scheme of things, geohazards involve any kind of hazards that revolve around soil. So earthquakes, sinkholes, landslides, mudslides, and any kind of mass wasting type of events. Those typically fall into the category of geohazards. Me personally, my research involves around landslides and some mudslides and sinkholes. So those are the geohazards I typically concentrate on. So what is an assessment? The idea is to say, first, if you can come across a sinkhole or a landslide that's occurred, you want to kind of to assess it, to assess it in real time or right after it's occurred to see what the extent is. And for the most part, that's for not only learning from the mechanics, but to actually assist in the restoration. So what's the extent? Are things still moving? Are things still evolving? And so you're trying to find out what is the current stability of those hazards. So that's the assessment of it in the here and now. The assessment overall, though, we want to learn from these. We want to learn why things happen the way they do. So what are the initiation stressors on a geohazard? What causes that geohazard to occur? And what are the mechanisms that are involved in it propagating once it occurs? That comes all under the assessment tag. For the prediction is once you kind of understand under what conditions these hazards occur, under what conditions and situations do they propagate. Once you can do some of those things, then you can start thinking about how to predict it and how to predict those things for early warning systems in the future. So my research right now specifically deals with using satellite data to predict, in this case, landslides is the biggest one, although we're starting to migrate into predicting sinkholes as well. But to predict landslides using satellite moisture data from some of the NASA satellites. And right now we're doing very well. And later on, we'll talk about the difference between landslide hazards or landslide hazard assessments and landslide susceptibility. And those are two different things. One deals with the static conditions and one deals with the dynamic conditions, thus being able to predict. And I concentrate mainly on landslide hazards. I want to be able to say what causes the landslides to occur so I can predict the occurrence of landslides in the future.
Awesome. So let's see. So how is the satellite data and the remote sensing techniques, how are they being used for the assessing and the prediction of landslides? And if you could give us some examples and the types of data that are being collected and analyzed, that would be awesome.
Outstanding. So the satellite data, for the most part, everyone thinks about satellites from or when we start talking about climate change and climate-driven hazards, we think about a lot of times precipitation. And precipitation has a big impact on the hazards. But the satellite data that we're looking at, for the most part, are satellites that are giving us ground moisture. And so they're giving us ground moisture and they're giving us temperature. So we surface temperature, ground moisture, barometric pressure, those types of things from the satellite data. And so now, if you can plot satellite data with time, whether it's soil moisture at a given depth or soil temperature at a given on a given day, if you can predict that or plot that or understand that information with time, then you can see that, all right, on a given point, the landslide occurred at some point, and you can see what were the conditions that were going on right before, during, and after the landslide. Now you put that kind of thing, like say satellite, say something like soil moisture. You put soil moisture into a regular old constitutive equation where it has soil moisture as the input. Therefore, and then say you have that constitutive equation or a stability model like a regular limit equilibrium stability equation, where the shear strength is a function of the unsaturated shear strength is a function of the moisture content. If you can show that the shear strength varies with moisture content, then you can show that the factor of safety varies with moisture content. And if you can show the factor of safety varies with moisture content, and you know exactly what day that a landslide occurred, and so you know what the factor of safety was on that day, then that gives you an opportunity to predict landslides in the future using satellite data.
Oh, that's awesome. That's awesome. Now the satellite data, I mean, I guess it would be certain regions that you're focusing in on or certain communities. Like, how are you parsing through all that?
Well, that becomes the science, the real science. So although it sounds nice and cool about, hey, bringing the satellite data and getting soil moisture, first off, we have to be able to take the satellite, for the most part, is giving us surface soil moisture. So, well, before we do that, we have to think about the resolution of the satellite data. Geotechs for forever and ever and ever have kind of shied away from using satellite data. It's because the resolution is so coarse. And what I mean by resolution, traditionally, satellite data comes to us in 36 by 36 kilometer pixels. So a pixel is 36 kilometers by 36 kilometers. At that point, it makes it very difficult to use it for site analysis. Well, one of the sciences that we're applying using machine learning specifically and other techniques, we're downscaling that satellite data from a 36 by 36 kilometer pixel all the way down to a 0.5 by 0.5 kilometer pixel. At that point, now you're starting to look at site level types of activities. And so that's the first thing, is to downscale the data down to something that looks like a site. The second thing is to take something that's inherently surface-based, so surface moisture, surface temperature, and then using various different infiltration models or propagation models to propagate that surface moisture all the way down to the subsurface. And so therefore we can get moisture with depth. And so now with that, with being able to first downscale it to something that looks like a site, and then be able to take a surface reading and project that surface reading or translate that surface reading down to a subsurface level. Now you have something that you can truly assess the stability of say a particular hill slope.
That's powerful. And how far of a depth are we talking on average?
Oh, right now, my current PhD students doing that I have working on this, we projected down to 3 meters, and so and I should back up. So here in Kentucky, we don't have at least in this, for the majority of the state, we don't have the deep-seated rotational slides. We for the most part, ours are translational, thin layer slides, because we only across our region and our state. We only have about somewhere between 15 to 25 foot of soil over our rock overburden. So for most part, ours are translational slides. So to be able to go down 3 meters, which is about 9 to 10 feet, then you're pretty much right. That's right. You're going to get it. You're going to get it pretty good at that point. And so we've been doing very well with that. As a matter of fact, I did turn out these techniques loose on some of the big slides, like the OSO slide or other slides around the country. And we still, even with using those big rotational slides, we can, and only being able to look down about 3 to 4 meters, we still have been able to look and see that there are very distinct patterns that when you get to the lowest factor of safety, that's when the landslide will occur.
Got it. Wow, that's incredible. That's incredible. Now, what are some of you hinted on some of these, but what are some of the main advantages of using satellite data compared to traditional methods of landslide assessment and prediction?
Well, traditional prediction methods were basically based off of, hopefully, at best, rainfall, some type of rainfall model. And they would use some type of antecedent rainfall. So they would say that once rainfall in this particular area reaches a certain intensity, so many inches per hour, so many inches per minute, or once it reaches a criteria or cutoff for cumulative rainfall. Once I reach a total of 46 inches or whatnot. Well, you can about imagine that if you use that, you don't have any soil parameters or soil characteristics at all into that, and you're just kind of basically lumping all soil into the one mass soil uniform bucket. So one of the benefits of using this, the satellite moisture is the satellite moisture is inherently site specific, so it uses surface brightness, and surface brightness is the function. So back up, the satellites themselves, the way that they get soil moisture all the way from outer space is they look at surface brightness, and they have a model that relates surface brightness to soil moisture. And the surface brightness is going to be a function of the actual soil type. But that's getting the 36 by 36 kilometer thing. Mm-hmm. To get the all the way down to the 0.5 by 0.5, we're using very specific site characteristics. How much sand, silt, and clay. What is the storage capacity of the soil? We're using very specific characteristics that are site specific. And so consequently, the first thing is that now I have a means to look at, and as opposed to looking at just one site in one area at one time, I can look at any site within, say in my situation, any site within the state of Kentucky, using my satellite data, it automatically will adjust itself according to the site conditions, because we've done other things to kind of verify it and calibrate it. But we can adjust, we can look at spatial data at anywhere in Kentucky. So that's the big thing that differentiates us from traditional methods, is we can look at spatial data. And because the satellites are going all the time, we get the temporal component as well. So we have spatial and temporal soil moisture data. So therefore, and when we put that soil moisture data into strength models, we have temporal and spatial strength. And if we have temporal and spatial strength, we have temporal and spatial stability models.
That's awesome. That's awesome. Can you talk a little bit about some of your ongoing research projects as they relate to Landslide, GeoHazard assessment and prediction, and then what are the key objectives and potential implications of these projects? I mean, I'm getting excited just hearing about this. This is curious to hear on your side. What are some things you should be excited about here?
Well, one of the big project that we were funded by NASA. So this is one of those kind of things that people don't think about when they think about the NASA type research. We were funded by NASA to use some of their satellites to do this various thing. And so the research that we're actually are embarking or pursuing, or doing, not pursuing, we're actually doing. The research that we're doing is that downscaling that I was telling you about, downscaling and calibrating satellite data to actual ground station based moisture content, temperature, and so forth and so on. So one thing is to downscale the data. The second thing is to calibrate the actual stability model, because what we found is just, using the regular infinite slope type stability models that you would find in your textbook are not adequate. So we're expanding those models and then refining them. And so that's part of the research. But then we want to bound or create boundaries as far as where landslides can occur versus where they can occur, based on, even if we know for specifically that landslides are really driven by moisture, we still have to look at things like vegetation, land use, the geomorphology. We still have to look at those types of things. And so we're adding all of that into our grand model to help us to predict, where these landslides would occur. And I say predict because a lot of you think about that soil. You say the soil moisture you're getting that from the satellites. That's not instantaneously. So it's a lag. It's about a 3 to 4 day lag. So you says, well, how are you predicting, Sebastian? How can you predict? We're using machine learning so we're using machine learning to take that soil moisture, because that's our driver, and we're predicting some days in the future. So that's the research. The other research is trying to see, using machine learning, how far in the future can we predict? And so that's one of the pieces of the puzzle. Because if we can predict 2 days, 3 days, 7 days in the future, using historical data, so you train the model using historical data, And then once you get your model trained, you predict in the future. So how far back do you have to go to train your model to predict in the future? And how far in the future can you predict? So that's research right there. But now the piece de la resistance is that once we get all of this done, it's the visualization. And so that's the last part of the puzzle. When you says where are you going to go with this and how is it going to be applied? My ultimate goal is just like you have your live at 5 and you have your we're predicting, this is how much rainfall for your 5-day forecast, right? This is your 5-day forecast. Well, I want to have a 5-day forecast with landslides so you could predict landslides 5 days in the future, and you would see on your map of Kentucky or any state, you would see the colors change from yellow or from green to yellow to red. And when it hits red, this is prediction that the landslide will most likely occur in this area. So not just susceptibility to say, oh, this whole area is susceptible to landslides. That's a susceptibility map. But I want to say, oh, a landslide will most likely occur at this location at this time. So that's where I'm ultimately going with this.
Wow. So no more weatherman or weatherwoman, right?
That's right. Yeah. The GeoHazard man. That's what,
It's like, instead of bring your umbrella, it's like, don't take that road this week, right?
That's right. Don't take that road. Or Farmer John, get the heck out of there.
Wow. No, this is great. So in your research, I understand you look at a deformation-based design methodology. Can you elaborate on that methodology, what it entails, and how it contributes to the field of geotechnical engineering?
Okay, well, now we're going to go, we're going to change up slightly. So that's my other hat. So I told you deep excavations and earth retention systems. That was another one of my areas of expertise, my areas of interest and research. Well, what has gone on with that is now it almost looks completely different from landslides. The connections is the fact that they're both stability problems. And so in the deep excavation in an urban area, you dig a deep hole and then or you will install earth retention systems, maybe a sheet pile wall, a secant pile wall, a tangent pile wall. You install some type of embedded wall. You dig down to a certain point. You put in some either put struts in or you put in tiebacks. You dig down to another level, put in another set of struts or tiebacks, and you keep doing that until you get all the way down to your bottom of your excavation. Build up your infrastructure inside the excavation, and then cover everything back up. All right. What happens when you do that is, as you're digging down, the walls will deform inward, and as the walls deform inward, the soil behind the walls will deform towards the excavation as well. As the soil behind the walls deform towards the excavation, any types of foundations, whether it's building foundations, bridge foundations, utilities, they will deform as well. And usually they will get damaged during that deformation. And so what we have done, or what my research it looks like, and so let me back up. So traditionally what has happened is that we've used a limit equilibrium-based method to build our retention systems. Basically, we want to make sure our retention systems are strong enough that they don't fail during the excavation. So we make sure that they're strong enough to resist the loads that are going to be imposed upon them. But that does not stop the deformations to happening from behind the walls. So the traditional method is, okay, make the wall as strong as possible. Go all the way through, and then do some empirical checks to see if we can empirically predict the deformations behind the wall. And then if we can empirically predict the deformations behind the wall, can we kind of make an estimate of the damage that we will see in the surrounding infrastructure? It's an iterative process that, okay, we're going to damage, we think we're going to damage the infrastructure. So let's go back to at the beginning and do something different with our designs. Okay, you go through the designs and you iterate this all the way to seeing if you're going to do damage. This iterative process, iterative process, iterative process. Well, my research starts at the back end and starts in the back end and works backwards. So I first say, and look, what's the tolerable amount of damage you're willing to accept with your infrastructure? And we can talk about why it is that you will be willing to accept damage in a little bit. But once you tell me what the damage you are willing to accept, then we will march backwards. And in essence, we will build a system, and we designed a system that will protect the infrastructure, surrounding infrastructure, from damage. And if we can protect, and by doing that, we automatically satisfy limit equilibrium. So we don't have to worry about the system being strong enough. The system will be strong enough because we won't cause any damage. So therefore, you're well within the limits or the limit equilibrium limits of your design. And so it is we say it's a deformation-based design because everything is based off our deformation. Ground deformations lead to building foundation deformations. Building foundation deformations lead to damage to the superstructure. And so we in essence limit the damage by limiting the deformations. And by limiting the deformations, we already know what types of loads that we can impose upon the system. So that's the deformation-based design approaches.
Thank you for that. Thank you for that. Now, what are some of the challenges or limitations that you've encountered using satellite data for landslide assessments and prediction? And how are you going to address these challenges in your research?
Right now, the biggest challenges is calibration, or downscaling and calibration. And so the way we downscale, we in essence, we find various different measures. So again, we use machine learning to find measures at a much higher resolution or a smaller scale than the satellite data. We correlate, so we upscale those. So if let me give you an example. If I have something like, say, percent, like the soil survey data, percent sand, silt, and clay on something like a 1 meter, 1 kilometer by 1 kilometer grid. Well, if I have that at a 1 kilometer by 1 kilometer grid, I will upscale those to say a 9 kilometer by 9 kilometer or 36 kilometer by 36 kilometer pixel. I then come up with a correlation between the satellite data and this upscale data. Once we have that correlation done from the upscale data and the satellite data, then we downscale it all the way down to whatever the original data we were correlating with in the first place. So one of the things is to find one of the challenges we have is to find data that we can upscale and downscale. So that's the first thing. And then the second thing is to have a ground station to eliminate the discrepancies or biases in our data. So we use ground station data to calibrate all of our correlations. So we do have so the problem that we run into is that we just don't have enough ground stations in certain areas to calibrate the data accurately. So those are the biggest things, and we're working on that by putting in proposals with the Kentucky Geological Survey and other big-time state agencies to specifically develop and ground stations for this issue of being able to calibrate and to simulate our satellite data all the way down to our local scale.
Spectacular. So those challenges or limitations end up being opportunities. So that's great.
Exactly.
All right. So apart from landslides, are there other geotechnical or geohazard applications for satellite data? I mean, I know you talked about karst and also surface depressions. What are some other things where we could use this?
So that was, one of the biggest ones that surprised us, because we were all saying that we didn't know if the sinkholes or the karstic environments. We know that those things are driven a lot by surface conditions and surface issues, but we didn't know if we would see some bona fide correlations between the advent of, say, a sinkhole and, say, moisture content or moisture content or any other remote sense data. And we found out we do, at least, unless it's one of those situations like in like an urban area where you have a pipe burst or something like that. But for a natural karstic environment, there is a relationship between things like soil moisture or precipitation and the occurrence of sinkholes. So that's been helpful. I have a colleague that has kind of peeked at the concept of looking at some earthquakes and how earthquakes may be able to correlate with various different parameters like moisture, changes in temperatures, changes in barometric pressures, the gravities, those types of things. But he's only peeked at it, so that's an area that it definitely can use a lot more investigation.
Okay, got it. Switching gears a little bit, as a fellow of the American Society of Civil Engineers, ASCE, and as a certified diplomate, geotechnical engineer, DGE, by the Academy of Geoprofessionals, how do these recognitions contribute to your work and your research in geotechnical engineering?
Well, first, as far as personal achievement, for me, I think I've always looked at when I was coming through the system, I would look at fellows and then later on when the DGE came on board, I would look at those individuals as individuals that were very knowledgeable. And so there were aspirations. I had always been inspired to be recognized by my peers as an expert within the field. And so now that those various different honorifics have been bestowed upon me, that helps me a lot of times when I have discussions with in particular with some of the individuals around my region, whether they're consultants or contractors or other academics. It is what it is. It lends more weight to sometimes what the things that I'm talking about. Versus me coming in as just being, Joe Blow off the street or this young professor, even though I guess I maybe not as young as I used to be, this academic, that's talking about things that may not be germane to the everyday goings and comings. When they see the honorific, sometimes what it does for them, it kind of gives them the impression or the comfort that you can actually have confidence in some of the things that I'm telling them about various different geotechnical issues and concerns. So it does lend itself to giving me a little bit more credibility when I talk in the public forums. So that's the first thing, and so it has helped me in those kind of things. And as department chair, and aspiring to go even further with my academic administrative pursuits, it also helps position me from just my credentials alone to being able to stand in the company of peers to say, look, yes, that I should be considered for this academic leadership position based off of my experiences, based off of my credentials. So it helps in that as well.
Spectacular. What advice would you give to students or aspiring researchers who might be interested in pursuing a career in geotechnical engineering, or even some even more specialized, utilizing satellite data for geohazard assessment? What advice would you give?
Well, I would step back to your original one, and that is for aspiring students that would be considering geotech. It is beyond what we do, even though a lot of our bread and butter is things like deep excavations, shallow excavations, and slope stability. All right, that's a lot of our bread and butter. But I would tell them to look beyond that, because most of the students today, Jared, they want to do more than just, I designed the POW foundation for the bridge, for that particular bridge, or the shallow foundations for that particular building. They want to make a difference. They want to see their life have meaning. And so when you look at geotechnical engineering and you look at this concept of climate change and climate-driven loads and climate-driven hazards fall well within our wheelhouse of geotechnical engineering. And so that concept of looking at how climate affects what we're going to be doing, foundations and the traditional geotechnical things, how it will affect what we will be doing in the future. That's one of the things. So that lets you make that difference. As far as being gee whizzy, think beyond just it's being dirt, right? How many times have we heard that from kids? It's dirt. We hear that from contractors. It's dirt. As a matter of fact, I remember having a contractor says, "Oh, you don't have to check this dirt. This is good dirt. I know dirt. This is good dirt," right? Dude, when I tell kids that one of the things that we have talked about is the biogeotechnics, right? Where we're using things like biocements and biomimicry to come up with foundation systems, or when we start looking at things like reutilization, utilizing and specifically utilization on things like Mars and the moon. When you start talking about not only how do you dig up the lunar or Martian regolith, but now you're utilizing it for a construction material, and you may also be utilizing it as a fuel source by if it's water ice bearing, strip out the water, strip out the hydrogen for fuel source. Those are things that we don't even think about. Yeah. So what would I tell that aspiring kid that's saying, I've heard about this geotech? I'll say, open your mind and dare to dream whatever impossibility you can dream. One of the things that we're pushing here at the University of Kentucky, as I've now been department chair, and this is going on my second year as department chair, is I say that the future is now. And the reason that I say that the future is now is the things that we used to see on Star Trek or Star Wars or any other science fiction thing, the Jetsons. Everybody likes to throw up the Jetsons. Those things are happening now. So that future is happening now. And you as a geotech, you get right into it as well. Biomaterials, reutilization. We haven't even talked about the concepts of some of the more outlandish of having engineered soil. When I say engineered soil, I'm not talking about the old concept of just compacting it at a certain density or something like that. But I'm talking about various different admixtures and products that now make the soil do things like the crazy sands and all of those types of things. All of that is what is within our sphere as geotechnical engineers. So dream of the future. The future is now.
I love it, because so many times when people think about geotechnical engineering, we're talking about, right? I mean, we're talking about like the pyramids of old. We're talking about, box culverts from antiquity, but like there's a lot of, and that's all great because it's still standing, right? But like there's some really exciting stuff that's happening now. So thank you for shining a light on that. Before we take our break, can you share any additional resources or references for listeners that want to learn more about using satellite data for landslide assessments and prediction?
Well, so if you're interested in using satellite data for any types of geotechnical phenomena, the first thing you have to do is learn about satellite data. And so I point you to the NASA sites that talk about just satellite data in general. But now, if you really want to get your feet wet and start looking at how you can use satellite data to track landform changes, land surface changes, we always talk about Google Earth. That's one thing, but the Google Earth engine, that is a different resource than Google Earth. Google Earth is, for the most part, a mapping tool. Google Earth engine is a satellite data repository. So go to the Google Earth engine, and you can get a good start on looking at various different satellite data, such as Landslides data. Some of the data I'm looking at, the SMAP missions, soil moisture, active and passive, SMAP. So all of that kind of data is at the Google Earth engine. And so you can see it right here now, and it does not require you to have any license, doesn't require you to pay anything. You can just download the app and get in there and start playing around.
Fantastic. Thank you so much. We're going to come back in just a minute to close this one out with Dr. Bryson in our Career Factor Safety In segment. But before we do, here's a quick word from our sponsor for today's episode, that being PPI.
Before we dive in, we'd like to recognize our sponsor for this episode, PPI, a leader in engineering exam prep for the FE and PE exams. PPI provides expert prep courses and study resources designed to help you pass the FE and PE exams the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. Check out PPI today at ppi2pass.com to see all the options available for FE and PE exam prep. Now let's dive into today's episode.
All right, welcome back. It's time for our Career Factor Safety In segment. In geotechnical engineering, just like many disciplines of engineering, it's important to incorporate a factor of safety into your design. But what about incorporating a factor of safety into your career? Today, of course, we're speaking with Dr. Sebastian Bryson from the University of Kentucky. Dr. Bryson, you've already had a very successful career. And when you look back in your career, what's something that you've implemented in your career to give yourself, let's call it a factor of safety in your career?
Learning what I tell my students all the time when they go from when we graduate and they move on. I tell them learn as much, about as much as possible. And so what has been a tremendous factor of safety, started with me all the way back at CH2M Hill, is be open to learning. That's the first thing. And so I tell them learn as much as about as much, but I also tell them don't compartmentalize your knowledge. So when you learn about, say, if you had some introduction to electrical engineering class, don't assume that class is only good for electrical engineering. Apply it to some other area. Specifically for us, now mind you, when we start talking about seepage, you realize that seepage in electrical engineering is very much similar. And so therefore, the various different techniques that you learned in, say, Introduction to Electrical Engineering, you can apply it to Introduction to Seepage. But it goes beyond that. You know, one of the things that you will find is your calculus classes, right? When I tell kids, I says, if I had to find an area under the curve, what would I do? And they says, oh, you take depending on the shape, you would use this equation where it would be, base times the height, or 1/2 the base times the height. I says, what about integrating? Because the integral is nothing more but the area under the curve. Or if I take the slope, if I want to find the slope at something, what would I do? Oh, you would take this. I says, what about taking the first derivative? So that concept of not departmentalizing your knowledge or compartmentalizing your knowledge. Use whatever you learn, wherever you learn it, to a particular problem. So do not compartmentalize your knowledge. Learn as much as about as much. When I was an engineer at say, CH2M Hill, now that's been many years back now, but I learned how to do site civil work. I learned how to do some light structural work, environmental work. Heck, I even learned how to do some mechanical engineering work. So consequently, that factor of safety, I never was without work. So when there was times that just didn't happen to be a geotechnical project that I was working on a site civil project, or I was working on an environmental project or a structural project. So that concept of learning as much, about as much, it allows you to be very adaptable to whatever your situation is. So those are the two things that I live on as far as, I do that even now. Try to learn even now as a department chair. So I'm the department chair of civil engineering. I'm also jointly appointed as a full professor in the Department of Earth and Environmental Sciences. So I'm a full professor with all the rights and privileges bestowed in the Earth and Environmental Sciences department. So I try to find out what's going on over there. So even as a department chair, I want to know what's going on in these other departments. In the architecture school, I try to find out and keep up with what's going on in that as well, so that I'm always learning as much as possible.
That is wonderful. Well, Dr. Bryson, thank you so much for coming on and for sharing all these great insights with us. You shared some great information, and I know this advice is going to be helpful for our listeners, helpful for me as well. If somebody wanted to reach out to you and find you, are you on social media or an email address you want to share we could put in the show notes? How can they find you?
Very much so. You can always find me at from the webpage. You go to Department of Civil Engineering at the University of Kentucky. I'm the department chair, so you can find me on the webpage there. If you want to directly contact me, you can directly contact me at sebastian.bryson@uky.edu. And that Sebastian is SEBASTIAN.Bryson, BRYSON @uky.edu.
Excellent. This is great. Thank you so much. Great to see you again.
Great to see you as well, my friend. Great to see you as well.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and/or questions. Please feel free to go to geotechnicalengineeringpodcast.com, where you'll find a summary of the key points discussed in today's episode, that being episode 77, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, we wish you the very best in all of your geotechnical engineering endeavors. Peace.